I liked what Zhu was saying. So Zhu was talking about what is truth. Now, my talk was entitled Truth is Winning. And it's a very interesting, I think, perspective. But this is actually not what my talk will be about, because I thought it was, I wanted to write it, and then I felt it was completely unworkable. So this will be about a topic I don't know that well, which is information geometry and statistical learning theory, and not about the nature of truth. But maybe later some people are interested in that. We could talk about that. Yeah, so feel free to correct me, or if you think there's some errors. Okay, so what is statistical learning theory? Well, we start with a distribution, and we take samples from it. So we have a distribution Q. Can you guys see my my mouse pointer? Can somebody confirm if they can see my mouse pointer? I can't see. Yes. Okay, great. So yeah, we have a distribution, and we take samples from it, and so a sample is a random variable is independently distributed on the sample space to Rn. So forget about this n. This should be big N, by the way. This is not important. So a statistical model for Qx is a conditional probability density function parameterized by a d-dimensional parameter space. And in statistical learning theory, we're interested in producing a best distribution Qn hat given the data Dn. Okay, so I hope so. There's my slides are a little full, so please maybe sometimes it's good to follow the slides. So there, I think Spivak should have put the slides somewhere so you can see them at your own leisure. Okay, so the central character of this talk will be the Fischer Information metric or matrix. So let's say we have a statistical model, so parameterized probability distributions, and the Fischer Information matrix is given by this expression. So it's a matrix. It's a d by d matrix. So d is the parameter, the dimension of the parameters. And yeah, you take this, you integrate over dx, you take these derivatives, w. It looks a little funky, but it turns out to be very important. And a lot of this talk will be about why it's so cool. It's symmetric and positive semi-definite, but we'll see that it's not always positive definite. Okay, what does this mean? It means it can have zero eigenvalues, EA, singularities. And that's sort of the topic of regular singular statistical learning theory. But first, we're going to talk about regular statistical learning theory. So let W0 be the W in W, so the parameters such that Qx is Pxw. And we say Qx is realizable if W0 is non-empty. And for now, we'll assume our models are realizable. There's also theory about non-realizable stuff, but okay, for now, non-realizable. We say a model is identifiable if this function is injective. So every parameter uniquely specified, or every distribution uniquely specifies a parameter. And a model is regular if it is identifiable and its Fischer matrix is positive definite. And it's singular if it is not regular. And we'll concentrate on the case where the Fischer matrix will be singular, meaning it will have non-zero, zero eigenvalues. Okay. A lot more, again, more equations. So please, I recommend looking at the slides because I know that you'll look at it and then forget, why is this wrong? Okay, well, okay, this should be dot, dot, dot. I thought I corrected this. Yeah, so this is a random sample. So this should be dot, dot, dot. And we define three important characters, the likelihood. So this is, given this sample, how likely was that sample according to the hypothesis W? Then we have the KL-divergence or relative entropy. I prefer relative entropy, but I'm going to follow convention here. So that's the distance from W to Q. So if I replace Q by W, what is sort of my error? And it's also known as generalization error. And then we also have the sample KL-divergence. Yeah. This should be a big X, I guess. Big Xi. Okay. All right. The maximum likelihood estimator principle says that we should pick the hypothesis Qn hat mammal, which has the highest likelihood. And I'm going to write down a formula. So if we take the log of the likelihood, so that's sort of the thing that you do often, it sort of doesn't matter if you want to maximize the likelihood, you can maximize the log, and this is often more computable. Then this is equal to the sample KL-divergence plus Sn, where Sn denotes the empirical entropy. So it's the entropy of Q. Of the empirical distribution. So maximizing the likelihood means minimizing the Kubic-Leibler divergence. So all these expressions are very closely related, and I imagine you sort of start getting confused. So let's concentrate on the more important point. Is the advantage of the MLE is that the likelihood does not depend on the true distribution. It's just like, what do we see? Does my hypothesis, or does a given hypothesis just predict it well? Yes. And now I'm going to give you an example. And I want to emphasize, don't try to, sorry, I'm going to use a different one because I think I actually have I have to recompile because I think there's some errors I actually corrected. Excuse me. No worries. All right. Maybe, there we go. Okay, so, sorry. So, yeah, this is a two-dimensional Gaussian. So I have X and Y, and the parameters are A and B, so in R2. And then this is the probability distribution, density distribution. And if I give random samples, the likelihood of A and B, so the likelihood that, how well are A and B doing, is this expression. Don't try to, this gets kind of, it's hairy, but it is very computable, at least. I just wanted to emphasize that this is, the expressions seem kind of intimidating, but really it's quite concrete if you get to it. So the sample KL-divergence is this, the KL-divergence is this, and the Fischer information matrix is everywhere, no identity. So it's quite simple. And this is a regular model. Okay. Now I want to talk about what is the importance of the Fischer information matrix. And I'm going to tell you sort of 6 facts why the Fischer information metric is so fundamental and so cool. And you probably know that the KL-divergence is very fundamental, or the relative entropy. Well, the Fischer information is sort of the curvature, or the second derivative. So it's the matrix, or it's the Hessian, right? The matrix of second derivatives of the Kubic-Leibler distance. Right, at the true parameter. So that's important. So KW0 is 0, right? W0 is a true parameter, so K is 0. But actually, the Hessian is non-trivial. So even though, so this is sort of the interesting part, is we want to study close to a true parameter. How does the geometry of the manifold, or of the space, the geometry, how does that look? Okay, I'm going to give you another example. This is sort of well known in statistics. Suppose we want to pick a prior on the parameter space W, and this will be important when we consider Bayesian learning theory. We'll get to that in later. And one important desideratum is that our prior phi W should not depend on how the pi xw are parameterized in any essential way, right? You don't want, I might have like a bunch of Gaussians parameterized by, I don't know, R, or R2, whatever, or some manifold. I don't want to have a slightly different parameterization and get a completely different prior. And so the Jeffrey prior has a cool property. So it's the square root of the determinant of IW. It has a very important, very cool property that if I have another prior, then they're related by change of variable formula. And that's the sort of, very cool thing about the Jeffrey prior. It's also related to the heat equation. That's kind of cool. And what do I want to say more? Yeah, so this means it's sort of, it's really well defined on levels of manifolds. Okay, next. Another famous case of Fischer information is Cramer-Rao. So once again, my slides are maybe too full. So maybe just ignore the middle part. So I start again with a parameterized distribution, parameterized by W, and we have a sample, and then we want to find an unbiased estimator, right? So we want to estimate so we get this data coming in, and we want to know what was the parameter, right? What I don't know. Now I'm gonna think about an example. I don't know, but the W is gonna, of course, determine how the distribution looks, and now we want to estimate it. And if it's unbiased, then the Fischer information gives us a lower bound on the covariance matrix. Okay, it's kind of complicated. So let's see in the case of D is 1. If D is 1, it gives you a lower bound on the variance. And that's, so think about the sample mean, right? That's an unbiased estimator of the mean. Well, this gives a lower bound on the variance. Okay, cool. Now we get to information geometry. So this is reason number 4 that Fischer information is so cool. And once again, I have a really full slide, so don't be intimidated. So we have the Fischer information matrix, and it defines a Riemannian metric on W. And this is a sort of complicated thing. And Riemannian metric is not literally metric. It's if on a manifold, it's like a parameterized inner product. And given a path on W, there's this formula that defines the length of that path. And I imagine this formula looks kind of intimidating if you haven't sort of seen this before. But I want you to just ignore this formula and think of it as a way to assign lengths to paths. And then the distance between 2 points is the length of the shortest path, or geodesic, between W and W2. Okay, and then we have the following theorem. So this makes it kind of concrete. The Fischer distance equals the symmetrized Kullback-Leibler divergence, right? So with 2 points, so 2 parameters, so 2 distributions, and it equals to symmetrized Kullback-Leibler divergence. So remember that the Kullback-Leibler divergence, relative entropy, is not symmetric. So that makes it not a metric. The Fischer information matrix or metric is a Riemannian metric, and its distance is symmetric. So that's cool. I think right now I want to get the floor open for questions. So we're 10 minutes in, 11 minutes in, and I want people to be able to ask me a question. Are there questions? Okay. I don't know. You guys can all. Okay. Yes.
All right.
Yes.
My question's coming from. No, maybe this is not the kind of question you want.
Go for it.
I don't know. I feel like put off by like having real parameters or something.
Yes. No.
Like,
yeah.
I think of like real parameters as useful when I'm thinking of them as probabilities, but
Yes.
I think here you have real parameters that are should not be interpreted as anything like probabilities. And I'm wondering if you have a defense of that or something.
No, I agree with you. So yeah, this is just my presentation of like sort of the simplest presentation of something I sort of, but not really understand. But my intuition is very similar to yours, that there's probably some generalization where most of these parameters are not necessarily real valued. And I think it's probably already partially known. Yeah. Are there other questions? Yeah, so let me some more. One thing is, I think if we would know how to sort of abstractly define entropy, that's sort of the key to a lot of this stuff. Yeah. Anyway, let's go on. Okay, so let me give you another example why Fischer information is so cool. And this is, I can't give too much details because it's a little intricate. But you can think of W as like being a parameter space of thermodynamic macro states and macro states, where the parameters parameterize conjugate variables. So a thermodynamic state is like a probability distribution on particles, and then the probabilities of like what the volume, what the energy are, and then the conjugate variables sort of constrain these. So these are the temperature, pressure, etc. And suppose I have two thermodynamic states, and then the square of the Fischer distance gives a lower bound on the total entropy prediction of a thermodynamic transformation into quasi-static limit. Oh my god. Okay, so it just means I start in thermodynamic states, I change a little bit, I make a little step, I let it equilibrate, I make another step, let it equilibrate again, make another step, let it equilibrate, and make very small steps. And then if I start in A and I end up in B, then that will give me some change of entropy. And then the square of the Fischer distance gives me a lower bound on that. And in fact, this story is more much cooler, much better behaved than just a lower bound. So what you should be looking is something called the thermodynamic divergence, which is sort of the square, the action, and you can give much more precise statements. Okay, but I wanted to give something that is sort of understandable. Okay, next. This is the last thing. So we saw examples in statistics, we saw examples in thermodynamics, and I want to give you an example in biology or evolution theory. So this, I learned this from John Bias, who I guess he's not right here now, but he will give a talk at some point too, I think. Yeah, I always recommend reading anything by John Bias. It's we should also do more Bayesian updating. So we have these self-replicating entities, so species, P1, Pn, I don't know, foxes, wolves, whatever, and they evolve according to a replicator equation. And so Fi is sort of the fitness of this ith species. And now we normalize. So we don't look at how many of a given species, but the frequency in terms of the total population. And then the equation becomes the change in the frequency is the difference between the fitness of the ith species and the mean fitness. Okay. And okay, so mathematically we have described a curve PT in some ambient parameter space, right? That sort of describes this evolving ecosystem of species. And there's a theorem that says, this is due to Fischer, and he describes it as the rate of increase in fitness of any organism at any time is equal to its genetic variance in fitness at that time. So you have to take this with a little grain of salt, but okay. But the concrete way of saying this is if you take the Fischer information, then that's going to be dp dt squared. So it's the square of the change. And this is going to equal the variance of f. So the variance of the fitness. So the square of the change is equal to the variance of the fitness. This is a little calculation. So we saw earlier that this square is also sort of the second derivative of the KL-divergence. So you could say sort of evolution is a sort of learning process, and the second derivative of that, the acceleration of that learning process, is equal to the variance of the fitness. I don't know what, it's what does that really mean? I think it's an interesting question. Okay, now, so we've seen regular, you could say information geometry proper, but this talk will the second part of this talk will be about singular learning theory. So once again, it's just an example, but it's not really about the example, so don't stare too much about it. It's a certain distribution, and it's a very simple 3-layer neural network. And I couldn't fit in a picture, but if you calculate, it's going to look like this. And we can check that if AB is 0, A times B is 0, the Fischer information is degenerate. And in fact, almost every statistical model is singular. Layered neural networks, normal mixtures, Boltzmann, okay, all these things are generically singular. I don't know what half these things are, but okay, anytime you have something that is a superposition of parametric functions, hierarchical structure, hidden variables, information processing modules, hidden knowledge, these kind of things, then you'll get a singular model. So this is just, in general, things are going to be singular. And there's a whole Japanese school that has been focusing on this information geometry, but sort of in practice, a lot of things are singular. And this is, okay. Now, this is a picture. Don't think too much about it. But if you have a singular manifold, a single variety, so sort of a manifold but with a singularity, then there's this whole theory of birational geometry. So this is called blow-up. So I have here a singular curve, and then I blow it up, meaning I find a sort of bigger smooth space in which this singular thing can sort of smoothly expand. I don't know if you can see it, but it's sort of you lift up this one arm of the singularity. And then I find a smooth manifold that maps to a singular variety such that they're sort of isomorphic except for these singular points. And this is called the birational equivalence. And birational geometry is all about finding invariance of this. And this is sort of going to be the key. Okay, we need to make a little detour, which is Bayesian learning theory. And a Bayesian learning statistical model is a statistical model. So Q, so the true thing, the parameterized thing, the parameter space, together with the distribution phi W, the prior on W. And then we define a Bayesian predictive distribution given a sample. So we Bayesian update the distribution. So this uses the prior. And yeah, and then we average. Okay. So now there's a following statement. So let this be a Bayesian statistical model and assume it's realizable. So using this birational geometry, the solution of singularity magic, we can define a birational invariant. So birational invariant is an invariant that doesn't see the difference between the singular thing and this blow up. Okay. It's quite complicated how to define it. So I won't be able to do this, but the important thing is there's this number. And if it's regular, then lambda is d/2. So it's a dimension. And if it's singular, it's smaller. Okay. Now assume that we have some estimate of the true unknown distribution QX based on the data set. Yeah.
Question.
Yeah.
Is this just for point singularities, or does this work for like entire singular, subspaces?
Yeah, there is. So the blow up, as I learn it, it's for point singularities, but there is a whole theory of there's a theorem by Hironaka that in characteristic 0, anything can be blown up, can be resolved. But I don't think you can only do it with blow ups. You need some other techniques as well.
Okay, thanks.
Yeah. All right. So the generalization error is just a distance to Q. And then we average that generalization error. And then the statement is this by Watanabe, this average generalization error is actually lambda over n plus something. And actually in here, there's a lot gets thrown away here. Actually singular statistical learning theory is really quite intricate. But this is sort of very simple case where we throw away a lot of things. So, okay, but in other words, this birational invariant is the learning coefficient. Wow, that's cool. If we have the Emily's estimator, and a similar story goes for what is called the maximum a priori estimator. Maybe you've heard about that. That's like the Emily, but you sort of allow in the prior. Then there's a similar story. There's some constant C. And when it's regular, then C is also d/2. But in general, C is lambda. So in singular situations, the Bayesian predictive distribution outperforms Emily. Okay, cool. So why do over-parameterized models work so well in machine learning? Well, I don't want to say this is sort of really true, but this is sort of maybe kind of gets, there are some problems, and I'll talk about this. But the learning coefficient is generally much smaller than d over 2. So even if you have this giant parameter space, high dimensional parameter space, lambda is much smaller. So the Bayesian predictive distribution can learn much faster than you would expect. Now, somehow the existing techniques are doing something like that, but okay. Okay, conclusion, singular learning theory. And I'm hearing a question. Information geometry forms a powerful framework for machine learning and artificial intelligence. Yeah, there are many more results in singular learning theory, which I think are very cool. It is quite technical, and I have to be honest, I really understand a very small part of it, but I think it's very important. In practice, it is hard to calculate the Bayesian predictive distribution. So this is sort of why you can't directly use it. And there are some approximation techniques, so especially variational Bayes or mean field approximation. But it's an open question if, how do you port this to these approximations? And it's also hard to actually calculate the birational invariant for large neural networks. So maybe one question to the crowd is, can compositionality help in calculating lambda for large neural networks?